Okay, let me go ahead and get started. So today our topic is interim analysis. And to put this in context, we're talking about studies that are clinical trials. And that they're clinical trials that are looking at comparative effectiveness, that is, difference between treatments or medications or drugs or whatever it might be. And the trials can be randomized trials or not. But the design of the study is such that it's going to be longitudinal. That is, patients are going to be enrolled over some period of time. And the with studies that are not necessarily clinical trials, but basically before you do a study, we determine the sample size and the statistical analysis. The thing about clinical trials is that it actually might take several years for enrollment and data collection. And typically an enrollment time period is specified. That is, are you going to enroll patients for maybe 6 months or even up to 2 years? So those are the decisions that need to be made before you start the study. In clinical trials, we have what's called a Data and Safety Monitoring Board, or the DSMB. And this board monitors patient recruitment, treatment administration, and can also ask for responses that are observed at different points in the time points in the study. The DSMB has the authority to stop the trial if, particularly if there's safety issues, or possibly if there's a situation where one of the treatment arms appears to be unsafe. That arm can be dropped from the study before the end of the study. But also the response on the primary endpoint may indicate that early termination of the study is desirable. And this can be either for a positive or a negative conclusion. And that's what we'll look at in the coming slides. So stopping a clinical trial involves 3 different concepts, and we've already mentioned the safety concept, that the DSMB has the power to stop a trial if there are adverse events occurring that are related to the treatment. Adverse events, that are not related to the treatment. If, say, a patient, falls and breaks their arm, that's not an adverse event related to the treatment. What we're going to focus on is stopping a clinical trial for superiority or futility. And by superiority, we mean that one treatment is better than the other. Futility means that there's no hope, in a sense, of finding a difference, of finding superiority or non-inferiority between treatments. And so the primary issue in clinical trials is not just time, but it's also cost. Clinical trials can cost millions of dollars. And so what they typically want to do, the investigator typically wants to do, is to take several what we call looks at the data before the end of the trial. And we're also going to determine how many looks we're going to take before the trial begins. You can't just, start the trial and then as you go along think, oh, now might be a good time to take a look at the data. This has to be specified beforehand. And so what we use is what's called group sequential methods. And so in other words, we're going to do interim analyses that are going to be based on time, or it can be based on the number of patients accrued or the number of events, which would be calculated the same way as the number of patients rather than time. So as a review, to understand why we're going to do this, is that when we do classical hypothesis testing, that is comparing two or more treatments, we're going to answer our research question based on samples from a population. And one of the threats to study validity is random sampling variability or chance. And that's where statistics comes in, that we want to quantify the probability of results due to chance. And the concept here is based on the idea that we can randomly sample from a population. And so to illustrate this in a diagram, if we have a population and there's a true population mean, and we sample from this population, then the question is, how representative is our sample of the population? And so if we were able to sample repeatedly, now obviously you can't do this in real research, but we can we can do it on a computer. But the idea is that over repeated sampling, if the population or if the sample mean equals the population mean, and we can illustrate this by taking, let's say, a random sample of my population here, diastolic blood pressures. And so if I have a treatment and control group, treatment to lower blood pressure, and these are my two arms, the treatment arm and the control arm, and I have a sample size of 5 here. And so I have a mean of 81 versus a mean of 86. And so in terms of hypothesis testing, is this 5 millimeters of mercury, I guess it's the units, is that a true difference, or is that a difference that could have occurred by random sampling variability? And so what we do is we specify a null hypothesis that there's no difference between the groups, that is, that the difference occurred just by chance. And then the alternative hypothesis is that there is a difference, and what we technically what we mean by that is the difference is unlikely to have occurred just by chance. But we're not going to be able to make an absolute statement about that, but it's going to be based on probability. And so when we do statistics, we assume the null hypothesis is true, and then we compute our statistical test, t-test or chi-square, whatever it might be. And then that test based on the t distribution or the normal distribution, the chi-square distribution, gives us a probability of obtaining the test statistic by chance. And then that's what we call significant. If it can be rejected, that it's unlikely to have occurred by chance, or not significant. And so a 2x2 table here that I'm sure you've probably seen before is the decisions that we can make versus the true situation in the population. And so the error that we're most concerned about is based on our statistical test. We say that a difference exists, but in the population, no difference exists. And we call that a type 1 error. And the probability of that we term alpha. And this is the probability equal to typically 0.05 in most studies. The other type of error that we can make, we call a type 2 error, and we call this probability beta. So this is the probability of concluding from our statistical test that there's no difference in the population, but in actuality, there is a difference that exists. And so it turns out then that, of course, if we take 1 minus the type 2 error, or 1 minus beta, that gives us the power of the test. In other words, the power that we have to make a correct decision. So, for example, in our illustration here of 2 different groups with a mean of 81 and 86, one way that we can test whether this occurred just by random sampling variability or chance is that we can essentially shuffle all the data, and then we'll take the first 5 observations and we'll call that the treatment, and we'll take the second 5 and call them the control. And so then we would compute the mean of each group, and we would want to see is that difference greater than or equal to a absolute value of 5. In other words, if we're doing a 2-sided test, then it could go either way. So we do this shuffling of the data a large number of times, and then we just count how many times the difference is greater than or equal to an absolute value of 5. And so I've done that here, but I've just done it 10 times. But you would do this, 1,000 or more times. And so then you just count up how many times you get a difference of 5 or larger. And in my example here, I've got 2, the 5.8 and the 6.2. And so my probability of getting a difference of 5 is 20%. In other words, that's my p-value. So in other words, if I was using the 0.05 level, then I would have to conclude that this difference occurred just by random sampling variability. So the issue comes, though, when we do multiple testing. And if we do multiple testing, what we end up doing is inflating the alpha error rate. And this, it's inflated by a factor of n times 0.05, where n is the number of tests. And I'm going to use 0.05 here because that's sort of the alpha error rate we could set at 0.01 or 0.001 or whatever we might want to, or even 0.06, but I'm going to use 0.05 since that's typically what's used. And so to control for multiple testing, a simple correction would be to divide our alpha error rate by the number of tests we're going to do. And this is the well-known Bonferroni correction for multiple testing. And one way that we might apply this is, say our study has 2 equally important hypotheses. Now, probably in the literature, you're going to see they're going to test both at 0.05, but technically that's not correct. So what we would do to make a correction for testing 2 different hypotheses is divide 0.05 by 2. And so then our p-value for statistical significance would be 0.025 for each hypothesis. And doing the Bonferroni correction, works if you have a relatively small number of tests. If your number of tests is really large, like you have 100 or 200 tests, then your p-value gets awfully small, and the Bonferroni correction becomes probably too conservative. So in applying these concepts then to hypothesis testing in clinical trials, what we want to calculate then is what is the p-value for statistical significance at each look at the data. And so typically what you're going to have a very small alpha error rate for your first look, and then at the second look it's going to be larger if you say doing 2 looks. So maybe we set our first one at 0.001, and then the second analysis would be 0.049. But it's a little more complicated than that for most studies. And so we're going to develop what we call an alpha error spending function. And basically what that's going to do is going to keep the overall rate at 5% or whatever you've set your significance level at. So in the group sequential designs, we're going to calculate stopping rules for each look at the data. And by stopping rules, are we going to stop for if it turns out that it's superior, or we're also going to calculate rules for stopping for futility. And basically, if you do a two-sided test with equal probabilities of the difference being either positive or negative, then the sum of all the cutoff values we want to equal about 0.05. And then the sample size, actually we can use the group sequential design to calculate sample size, but typically the way that it's done is you determine your sample size based on the test and the difference you want to see at the end of the study with an alpha error rate of say 0.05. In other words, if you were doing just one test, what would the sample size at the end of the study, one test at the end of the study, what would your sample size be given your alpha error rate? So I have a little bit of theory here. I'm not going to go through this in any sort of detail, and this is just for say two groups that we're going to compare, a treatment group and a control group. And basically, what is used in calculating this is a Brownian motion process. Brownian motion is the theory was developed in the context of particles, but some people a lot smarter than I applied that to hypothesis testing, where you're taking more than one look at the data. But basically, the equation there I have of theta, that's the difference in, say, the means of the two groups divided by the standard error of the two, of the difference of the two groups. And so we're going to compute our boundary values based on a specified function, spending function, and alpha value. And then we're going to use this to determine the p-values at each look of the data. The spending functions have been developed, been around for some time, for quite a while. The idea, though, that is if at any one look our alpha level crosses the boundary at that given time point or number of patients, then we're going to stop the trial early for superiority. And basically, the important concept here is that the alpha spending functions are going to all add up to about 0.05. Okay, so then there's two primary spending functions that you see in the literature. There are more than this, but these are probably the two most famous, the O'Brien-Fleming and Pocock. And the O'Brien-Fleming one, the 2 minus 2, what is that, phi, I guess, stands for the normal distribution. And so we're using the normal distribution to calculate our alpha error rate. And so the z sub alpha 2 there is the z for significance at an alpha error rate, a two-sided alpha error rate. And then that's divided by the square root of the time at which you take the look at the data. You can do others, there's others as well, but these are, the O'Brien-Fleming is the one that's used most often. And so this is what the boundaries would look like using the O'Brien-Fleming and the Pocock boundaries. And you can see that with O'Brien-Fleming that you have a very large z-value or a very small p-value at the beginning, and then as you get closer to the end or your last look at the study, which would be the final analysis, the p-value gets smaller, closer to it'd be less than 0.05, but something smaller than that. So you get this decrease in the size of the boundaries as you take each preceding look. The Pocock one is more the same across all looks. In other words, the p-value is more or less the same for each look at the data. So here's what we mean by this. So I want to give an example here. It's actually easier to understand in graphics. So this is going to be for a two-sided t-test, and so we have our boundaries set. And so what this means that as long as we're between the two boundaries, we're not going to reject the null hypothesis. And if we get out here to the very end of our study and we're still somewhere, our z statistics or p-value is somewhere in here, then we're going to fail to reject the null hypothesis. On the other hand, if at some particular, and this would be an example of failing to reject overall looks, that our z statistic is all doesn't fall outside the boundaries. And for a two-sided test, this would be it would be the same whether it's positive or negative. But on the other hand, if at any particular time point our test statistic falls outside of the boundary, then we're going to, at that point, reject the null hypothesis and we're going to stop the study. And I just put the rejection here on the lower boundary, but it could be on a two-sided test, it could be the upper boundary as well. So here's an example of how this looks from a interim analysis statistical package. And that's actually what this comes from, the one that's most common used called PASS, P-A-S-S. And so what I've set up here is to look at a difference that could go either way, a difference of plus or minus 0.5. This variance is 1, and I'm calculating this for a power of 90%. And so you can see the boundaries here and the areas of rejecting the null hypothesis is either up here or down here. And so you can see that in this case, the boundary p-values all in this case add up to about 0.05. And then it gives the z-values over here. So you can see it's a very small probability at your first interim analysis, and then it gets larger as you progress towards the final look at the data, or the time when you do the final analysis. So in terms of looking at sample size, if I was going to do this kind of this particular study, it also gives me the target sample size I would need at each look to achieve that. And so you can see that in this case, at the last look, or at the last analysis data, I would need 83 patients or subjects in each group. So here's an example for a one-sided test. So we have an upper boundary here. So that's just, so we're looking at just this area here as the rejection region. Even if the z-value is negative, large, a negative value like -4.3, and it falls down here, that doesn't matter because we're only doing a one-sided test. And so we might get to the end of the study like this, and we would then fail to reject, even though as I mentioned, if this last look is even down here in the large negative region, we would still fail to reject. But on the other hand, we might have the situation where, say, at the last look at the data, we surpass the boundary or look out, or the test is outside the boundary of rejection here, then we would reject the null hypothesis. So here's the one-sided test from the software and the information that it gives you. The same things here, or the same concepts here. Let's see, do I have a question and answer here? Oh, okay, let me finish and then I'll come back and deal with these questions. Okay, so anyway, for the one-sided test, you can see that with a power of 90%, that my p-values actually are larger, or sum to larger than 0.05. And then the corresponding z-values for each of those looks at the data. But you can see here that if I was doing just a one-sided test, I actually need fewer. Remember that a two-sided test, I needed 80 some. Here I only need 70 some. So in terms of looking at, see here. Oh, okay. Yeah, so those add up to actually larger, more than 0.05. So we can then also look at not only efficacy, but futility. In other words, is there a point where it's sort of useless to continue the study? So we set up boundaries that look like this. So we have our two-sided test here where we can reject the null hypothesis, either if it's positive or negative. If our test falls in here, we continue, but we can set it up so that if our test falls in this region here, then we can fail to reject or accept the null hypothesis. And so basically, when we look at both efficacy and futility, so here's, we would reject it there. We could reject it down there, but if we find that our test, our probability falls, or in this case, our test statistic falls, and they accept the null hypothesis, then we would stop the study at this point. So basically, and it can be either positive or negative again. So what we need when we do both efficacy and futility is that we have, as we mentioned, we have the alpha error spending function for efficacy, but now we need a beta error spending function for futility. And so, again, this is important in large, expensive trials, that if it looks like there's not going to be any possibility of rejecting the null hypothesis, then you don't want to spend any more money or time on the study. So here's, again, an example of software that illustrates looking at efficacy and futility. And so I've sort of set up the thing here, two-sided test, power of 90%. And so if we have the situation where at one particular look at the data, our test statistic is statistically significant, then we can stop the trial. Again, if it's a two-sided test, on either boundary. On the other hand, if we find that at that particular look that our test statistic falls in the futility region, either on the positive or negative side, then we could also stop the study for futility. One thing I want to point out here is you can see that when you do a futility as well as superiority, that you're going to need more patients. And so here we have, we're going to need 90, 91, whereas if we were just doing superiority, we only needed 83. So what I want to take the rest of the time to do is to talk about software, because you actually want, probably want to do this on find some software that will do this for you, because the calculations are fairly complicated. Anyway, so the data that we can use to do this on is any kind of data, whether it's means or proportions, odds ratios, survival, or do it on counts, where we have a Poisson regression. Use Poisson regression, we can calculate alpha error spending or a beta error for futility. So the information that we need to do this is, of course, the alpha error rate and then the power. And the power is 1, as I mentioned, is 1 minus beta. I might mention that the beta error rate that most studies go with is 20%, or a power of 80%. Now, some studies do a variation of that, where the beta error rate is smaller, like 10%, so your power is 90%, or the beta error rate is 15%, or you have 85% power. So typically, that's what you'll see is a beta error rate between 10 and 20%. Usually, and I can't think of any study I've ever seen that goes below 80% for power, or a higher error rate than 20%. So given that, then we also need an effect size. In other words, what is the difference that we want to be able to detect between the groups, the treatment groups? And then we need the variance of the effect size. And then, of course, we need to know what statistical test we're going to do. So the examples I've given so far, and the ones I'm just going to focus on, is just a simple t-test between two groups for means. So the software, the one that I've already showed you examples of is PASS. I assume that stands for power and sample size. That's put out by NCSS Software out of Kaysville, Utah. The other two that I'm going to go over is SAS, and the routine there is SEQ design. And then in R, which I've never used R for doing interim analysis. At least in my view, it's a lot more complicated because you actually have to write the code. But the program is GS design. So I want to give you just an example here of what PASS looks like. And so if you're doing group sequential testing, you have all these choices here of doing means or odds ratios, proportions. And as I mentioned or implied before, you can do this for non-inferiority as well as superiority. And so you have a lot of different selections you can do here. And so the information that you have to put in is fairly straightforward. So here's an example of the one that I've already showed where we're doing efficacy and futility. So my power is 0.9, the alpha error rate is 0.05, and I just, have a mean here in one group of 1.5 and a second group is 2.0, and the standard deviation is 1. I'm going to take 4 looks at the data, and the 4 includes the very last analysis that you would do, and then that's equally spaced, or it can be non-equally spaced. I'm going to do two-sided efficacy with futility, symmetric, and then I'm going to use the O'Brien-Fleming procedure for calculating my boundaries. And then I also tell it that my design beta is 0.1, 10% error rate. And so what I have in terms of choices here is the one that I did before. I did a two-sided efficacy and futility. And then you can do either symmetric or asymmetric. And most of the time, what you see is symmetric in papers because they're not usually doing asymmetric. And this is what asymmetric means over here, that asymmetric means that you, for example, that you can use one boundary to show efficacy and the other side to show harm or futility. Okay, so SAS is, at least in my opinion, a little bit more difficult to use because you have a lot of options. But there's a paper here on the SAS SEQ design, and I've given at the end, I've given the reference or the link for this study if you're interested in seeing if you're a SAS user. So in going through or setting that up in SAS, then you have the proc SEQ design, and then you have all kinds of options that you can put in here. And so you have the boundaries, the p-value, whether you want to do plots. Then you have set your alpha and beta error rates, whether you want to do an upper two-sided, and then the method, which is going to be either O'Brien-Fleming or the Pocock, or there's, like I mentioned, there's others that are used, although as I mentioned, the O'Brien-Fleming is the most common one. So that's what SAS would look like if you're a SAS programmer. Then it's basically putting in all the options that you need. And then you put in whether you're doing regression or logistic regression or proportional hazards. So in terms of getting a plot, you see you get a plot that looks similar to the one that you get in PASS, where you have the rejection regions, where this is a two-sided test at alpha 05 and power equal to 90%. So again, you get a similar looking graph in SAS. Okay, then in R, the program is GS design. And you can do all kinds of things with this again, but this you have to program each of the statements. And so you can also do O'Brien Fleming or Pocock designs. I believe there's some other ones that you can use for that. And then you would can also then plot the graph. But this is the if you used every possible thing here that you want to look at in GS design, you could put all that in. But the ones that you need, or at least the two that you need, are the K. That's the number of looks you want to do, the test type, and then the alpha and beta levels. Although what's in there now, the 0.025 and the 10% beta are the defaults. So, as I mentioned, K is the number of analyses. And then the test type. So again, this is similar to what you can do in both PASS and SAS. 1 is one-sided, 2 is two-sided symmetric, 3, 4, 5, and 6, and so on, depending on what you want to do. And as I mentioned, the default value for the type 1 error is 0.025. If you want something else, then you can put that in. Then the same thing with power. And then you can plot the boundaries and the corresponding cutoff points. Actually, in a couple of plots that I looked at where that was not generated by the computer, I basically, what I did is I calculated the boundary points, and then I just programmed those in a simple plot program. But anyway, you have all those possibilities. So this just gives an example of our code for cutoff values for a 3-stage trial. So you can see that it can get fairly involved, and so you sort of need to know what you're doing to program in R. And I might add that the GS design information to do the programming, the different things, is like 186 pages long. So there's a lot you can do in R. So I've put a few references in here. The ones in the journal are pretty heavy mathematical, so you may or may not want to sort of look at those. And there's probably more recent ones, but the Chow and Wu book from 2008 is pretty good. It does have some technical, but it has just sort of good narratives as far as describing what they're doing. And then the last is the link for the SAS paper on SEQ design. So I want to thank you for your time, and let me go to the questions here. The idea of having beta set at 20% is largely tradition, just like 0.05 is. And so basically the beta error rate particularly in medical studies is set usually at 0.2, but oftentimes you might see it set at 0.15 or 0.1. If you get much lower than 0.1, then the number of patients stated becomes larger than you can probably afford. Yeah, the Z value at the cutoff yes, depends on the sample size, and that's what is calculated for you in the in the software, so that you can look at the sample size that you would need at each cutoff, at each look at the data. And yes, I'm going to send this presentation along to the folks at Georgetown, so you have available for. I think I've forgotten to do this for the last couple of sessions, so you might get 2 or 3 sets of slides here for past presentations. So I then want to mention that this is the last statistics seminar for the year. We'll take the summer off, and then we'll start again in September. So whatever the 3rd Friday is in September is, we'll start again. So let's see, we have a couple more questions here. Oh, they were there before. No, so the stages refer to the number of looks that you want to take, and no, you can't generate those after the data is collected. That's something that has to be done before you start the study, and before you enroll patients. As I mentioned, I think earlier in the beginning, you can't, as this study goes along, then all of a sudden decide, yeah, okay, let's take a look at the data. One thing I didn't want to go into, that you can also use this for, in taking your look at the data, is to recalculate sample size. Now that's is not always viewed positively by all parties involved, but it's something that is sometimes done. Okay, and then so the desired effect size, basically you get that either from previous published studies that are looking at the same outcome that you're going to look at, or maybe you've done a pilot, or somebody has done a pilot study that gives you an idea of the difference in the variance of the difference, whether it's a difference in means or difference in odds ratios, whatever it might be. I know that in Cohen's, he uses, gives you values here for what's a small effect size, what's a large effect size. Usually I don't really go by that, but in effect, the effect size that you want to get at is something that's clinically meaningful. And there have been studies published that I've seen that it's obvious that they've chosen a large effect size, which means that you don't have to have as many patients, because they probably knew they couldn't get. So they had a really large effect size of 0.5 or greater. I guess that's my cutoff is. I usually take a effect size of, say, 0.1, 0.15, or 0.2 is what you would maybe want to look at. But that's arbitrary, and so you can decide that. But in my view, it's something that's decided by the investigators, by the clinicians, because they are the ones who know what's clinically meaningful. And that's, I guess, the criteria that I think you should use for determining an effect size, is what's clinically meaningful. So it might be that you have an effect size that's so small that it's clinically meaningless, or so big that it's also, I mean, you don't know really what it is, so it's also kind of meaningless. Okay, and let's see, is that okay? As I mentioned, I will be sending these along. This slide, as well as I think the last two sets of slides I forgot to send. So let me see here if is there one more question? Yes. Oh, okay. Okay, that's iSPIs. I'm not familiar with that. So, and that's actually a topic for next fall, is I'm going to look at Bayesian statistics and how you calculate and do this from a Bayesian perspective. So that's something that I'll have to look into for myself as well. Let's see, and there's maybe one more here. Okay, all right, well, fine. I will then see you next fall. And as I say, I will be sending along the slide sets here from the last couple of sessions. So thank you for your time and attention, and really appreciate your listening in, and hope that these are helpful to you.